All right, recording is started. So welcome to Wednesday. I have a lab lined up for you guys today. Before we get to that lab, I need to tell you the physics of setting up standing sound waves and pipes, because that's what this is going to involve. I've got some PVC pipes. I'm going to dump this in water. I'm going to take a tuning fork and strike it above it. And at certain intervals, it'll set up a standing sound wave. So I need to tell you guys about that physics first. Okay. Go into this. The way we're going to do this lab is the way we did the last one, the pendulum lab, which is we'll do this demo style. I'll do this up here. I don't really like doing labs this way, but because it's good for you guys to get your hands on these materials too, and think critically about what you're doing. But COVID is running pretty rampant right now, so try to keep you guys isolated. There's one more college physics problem I gotta go hit, so we'll do this after the lab. And then I'll go do as many of there were a few AP classroom questions that didn't get to yesterday, so try to hit some of those too. So first, standing sound wave. Well, let's go review just standing waves in general, maybe on a string. Now on a string, of course, this would be a transverse wave, which is not exactly what we're doing today, but it's a good starting point. You guys saw a video demo on this last week. Remember, no, not all waves on a string will be standing waves. A standing wave is a special case where you have these nodal points. Right? Remember, if you touch the standing wave, say this node right here, it doesn't actually affect motion because this node doesn't move. But there are specific intervals where you can set those up. It might be like, this could be the fundamental frequency. How many wavelengths do you see right here? Half. Yeah, that's half the story. I see a crest, but no trough. Right? Here's one full wavelength. Then one full shaker. And yep, 1.5, 2. Okay, so it goes half, 1, 1.5, 2. Okay, so there's like a pattern setup, right? Something like that. Okay, so that's for a transverse wave, say a wave on a string. But we're going to switch over and look at pipes and like sending a sound wave down a pipe. So I'm going to get some pipes going. I'm going to draw 4 vertically oriented pipes. Right, so one at a time. Say I take a tuning fork. I have to show you guys these tuning forks too. Okay. So I've got a box of tuning forks. Got most of them in here. So these numbers have, these tuning forks have numbers stamped on them, and letters that correspond to musical notes. Right, so they say C, D, E, F, G, A, B, C. Okay. Take the smallest one. It says C, and then it has 512. That's 512 what? Hertz. Yeah, 512 hertz. Okay. Now, side note here, I'm put my screen over, show you guys something here. There are different standards for tuning musical instruments or establishing like what notes are what. The main standard you see is like A is defined as 440, and on this scale, the corresponding C note would be like 523 hertz. Like there's a piano back there. If you hit the C note, that it's going to be 523 hertz. Okay. But oh wait, did I share my screen? Okay. So if you're watching the video, okay, I've been referring to this for the last 10 seconds. So there you go. Okay. But these tuning forks are using a different standard, so it's off a little bit. It says 512. Okay. I did find also another tuning fork I dug up back in the lab. It says also 512C, but they do sound different from each other. So here's the one from the box. Here's another one.
Very different.
Yeah, it's a little bit higher pitch. Sounds off by, I don't know, maybe a half step or something like that. So these are off, maybe a little bit. That might throw off our experiment. That's just thinking ahead a little bit. That's what a tuning fork looks like. That's what it sounds like. And yeah, a few caveats there. Okay, but here's what we do. Let's go back to some pipes. Okay, let's say I take one of these tuning forks, which looks about like this, and I strike it above one of these pipes. Or it doesn't necessarily have to be a tuning fork, although we'll be maybe kind of air blowing through, setting up some kind of standing wave at some point. Now, if the pipe is open at both ends, that could be maybe like a lot of wind instruments, maybe a flute, recorder, maybe some brass instrument. A lot of instruments have like air flowing through some tube, effectively something like that, right? Now, the physics rule for setting up specifically a standing wave inside a pipe is where it'll resonate, and you guys will hear where it resonates when we do this lab in a few minutes, is that the ends, the open ends, have to be low pressure points. Remember, sound is a pressure wave, right? And then somewhere in the middle, you could have a high pressure point. Okay? And the fundamental frequency scenario would be if you have a high pressure point in the middle, and then it gets lower pressure as you go out. Every one of these dots sort of represents like an air molecule, think of it that way. Okay. See how it's like low pressure, high pressure, low pressure? Okay. Now, what I just did, that took a long time to draw that. So like dot, 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 dot. And then if your picture isn't very good, then the person trying to read and interpret it, well, it's hard on their end to figure out what's going on too, right? So it's really common to represent longitudinal waves with transverse waves, even though they aren't really transverse. It's low pressure, high pressure, low pressure. What I'm going to do is with pink ink is draw an abstract representation of this longitudinal wave with a transverse wave. So the most common standard you'll see is low pressure treated as an antinode and a high pressure point treated as a node. Okay. You can also have the reverse standard. I'm going to cross this over on itself, just make it even more obvious. Kind of like if this were a string vibrating up and down, this would be like a nodal point. You go like that, right? So sometimes you do this in terms of pressure, so you can make this the node and this the antinode, but most often you'll see it the way I just drew it. So this length of pipe, I'm going to call L. L is the length of pipe. Okay. How many wavelengths do you see from here to here? From this crest to this trough, that only represents half a wavelength. This could be half of a wavelength. Okay? If you had to get wavelength in terms of the length of the pipe, could you just cross multiply this 2 and say 2 times the length of the pipe would be the wavelength? Okay? If there was some context for that, you guys could do that, right? Okay. What's the next place you could set up a standing wave? Let's say you picked a different tuning fork. Maybe this tuning fork is like smaller. Now, if it's a smaller tuning fork, see how I drew this one physically smaller than the original one? Is that going to be a higher or lower pitch? A higher pitch. And since speed is equal to wavelength times frequency, if you have a higher pitch, and the speed of sound is just whatever it is, so constant. Okay. What happened to the wavelength? Yeah, it gets smaller, it gets shorter. Okay. And maybe you picked some scenario where it happens to set up a standing wave that looks about like this: high pressure point, and some other air molecules doing their thing. It's like something like that, right? Kind of hard to see and interpret, so I'm going to represent this longitudinal wave that I just drew with a representative transverse wave. So node, antinode, node, antinode, antinode, node, antinode, node, antinode, like that. So now this length of pipe, L, is how many wavelengths is that?
1.
It is 1. This crest to this crest, that is exactly 1 wavelength, isn't it? Okay, so this would be like the fundamental harmonic and maybe the second harmonic. And for this scenario with pipe open at both ends, second harmonic happens to line up with exactly the length of the pipe. Okay. So I could keep on going, but I'm going to pause it right there and just show you guys this poster that has the answers on it. Okay. So this is one of the ones hanging from the, or wait, is this hanging from the ceiling? Yeah, I think it is. Oh, we've got, oh, that looks like that. That looks like that. Look at that. Fundamental, second harmonic. Okay. And then we've got half a wavelength, 1 wavelength, 1.5 wavelength, 2 wavelength. Okay. Actually, this follows a really similar pattern to the string, doesn't it? It's kind of like that. So you can keep going on like that. What if we change this up a bit? What if instead of having a pipe open at both ends, we closed off one of the ends? Like this. Just close off that pipe. Hey, this could be like now if you send a sound wave into here, this might be like blowing into a glass bottle. Right? You guys ever blow into a glass bottle? It might resonate at a certain pitch. Like, let's try this for a couple of setups here. Okay. Now the physics of a pipe closed at one end. What kind of pressure do you think is at the closed end? A high or a low pressure point? High pressure, all those air molecules like bouncing off the end. Right? And I'm going to have this as water, right? I'll have a pipe submerged in water, and I can lift or lower the pipe to effectively change its length. But this water will be more close in. Yeah, but there's going to be a high pressure point here. So if you saw a bunch of air molecules, it kind of Now, a fundamental situation might look something like that. Got low pressure on the open end, just like before, and a high pressure point here. Right. Now, if I try to represent this with a transverse wave, got node, antinode. Now this one's real gradual, so be really careful about drawing this. This curve here. Okay. So yeah, that is a little slice of a sine curve. Okay. So the length of this pipe, see if you guys get this. What fraction of a wavelength is that? It is a quarter. Yeah, a fourth, quarter. That one's kind of tricky. A lot of students miss that, but I heard a bunch of guys say like a quarter or a fourth. Yeah, exactly. And then if you needed to, you could say, well, 4 times the length would give you 1 full wavelength. Okay. So if you have like 4 of these to go from this node to this antinode, okay, that's a quarter of the story. All right, so that would be like the fundamental frequency that you could set up with a pipe close to one end. Okay. Now, say I pick a smaller tuning fork or a longer pipe, either way. Imagine like now, remember the physics rule is you always have a high pressure point at the closed end, a low pressure point at the open end, but maybe about 2/3 the way up, you might run into another high pressure point. And then like this. Like that, another longitudinal wave. And now why 2/3 the way up? Well, because the next place it could resonate to follow all these rules of high pressure, low pressure. What's the transverse representation look like? Oh, it would look kind of like this, wouldn't it? Ah, you see that? So now the length of this pipe is how much of a wavelength? Yeah, 3/4. Huh. And if you had to, you could say something like, well, if I had an extra third, so I got 4/3 of length, that would bring me up off to the full wavelength, wouldn't it? Okay. So how about this here poster I pulled off the internet. Oh, look what we got. A quarter of a wavelength, 3/4. And then the pattern goes 5/4, 7/4, 9/4. Okay, so there's a pattern there, but it's not like it's not like open at both ends, and it's not like the string. Okay, guess so. You know what? I bet you could do too. Normally, you'll see like in a physics textbook, you'll see this scenario or this scenario. Do you think you could have a pipe closed to both ends? Maybe you're like in some underground bunker tunnel that's like shaped like a pipe or something. You're like, you hear your voice echo back and forth. What do you think the rules would probably be for that? Do you think it'd be like high pressure, high pressure? That's it. Yeah, I bet it would be. Okay, so you guys got this lab page. Okay. So our goal with this lab is to figure out, can you calculate the speed of sound? Okay, that's the end goal. Try to calculate the speed of sound. Okay. The very last line says so many meters per second. Like this formula, explain this from the end backwards. It says speed is equal to wavelength times frequency. Right? That's going to be the very last step. Okay. And you know what the speed of sound is? It should be approximately. Does anybody remember the number?
140 hertz.
Yeah, about 340, 343, somewhere there. Meters per second. Speed of sound, right? Okay. So if you said 340, 343, like anywhere in there would be good. This is just a ballpark estimation, right? It depends on the temperature, blah, blah, blah. Okay, so where are we starting this thing? Well, there's going to be some tuning fork, and I showed you the tuning forks have the number stamped in them. Are they exactly accurate? Not exactly, but we're going to know this frequency. That's the point, right? So we're going to know this number right away. We're just going to read it straight off the fork, okay, and assume that it's true, just like everything on the internet. Okay, then, if only we had some associated wavelength, we could multiply this together and get the answer. How are we going to do that? Well, take a look at the setup. I'm going to draw over this just to make these lines darker, especially for the video. Look on the video. Well, actually, it's not too bad on the video. Okay. But we got this, there's some kind of beaker or flask full of water. We're going to have this pipe that I can dunk in here. Here's the water level, like right about here, water level. And then strike a tuning fork above it. Okay. And what you guys will hear just in a few minutes, so listen for this, is that as I raise and lower the pipe, which effectively changes this length here, okay, there's gonna be some place where it resonates, and this is what it'll sound like. It'll be like loud, like resonating. And that length we'll call L1, like L1. And remember how that corresponds to a quarter of a wavelength? Well, for the shortest length of pipe that would happen, it would be like a quarter of a wavelength. Now I just drew in a pink transverse wave because it's not really transverse, but it's easy to interpret, right? Okay, now what I would think at this point is, well, couldn't you just take that quarter of a wavelength, whatever L1 that corresponds to, quadruple that L1, and that would give you the wavelength, and then boom, boom, done? You could do that, right? And that's actually not too bad an idea, except, well, for one caveat I have not told you guys about, which is that the low pressure point doesn't actually correspond with exactly the top of the pipe. It actually extends a little bit beyond it. How much? Well, that depends on the diameter of the pipe. Like you could do this whole calculation. So that's one way to take that into consideration and get a little bit more accurate answer. We're not going to do that though. We're going to do a different method where going to instead take this pipe. Here's the water level, and extend it upward until I hear a second place that it resonates. And so same tuning fork, same tuning fork as before. Right, strike it, just bam. And the next place that it resonates, well, wouldn't that be like 3/4 of a wavelength? It's like this right here. And we'll call that distance L2. L2. Right? Right, so we've got a quarter of wavelength, 3/4 of a wavelength. Now, if you subtract the two, L2 minus L1, which is what this step says to do right here, take the difference. How many wavelengths would you have at that point? What's 3/4 minus 1/4? Half, right? Yeah, half a wavelength, right? And the advantage of doing that is that however much the wave actually extends above the top of the pipe also gets subtracted out, doesn't it? Ah, that's why we're doing this method. Okay, so once you have half a wavelength, couldn't you just double that? That's exactly what it says to do in this box. Wavelength is 2 times the difference, so L2 and L1. Okay. And then you can feed it into this formula to get the answer. Okay, that's what we're doing. All right, so pick the first tuning fork. Actually, I'm going to use this big one that I pulled not from the set because I tried this last class, worked pretty good. This says 512 hertz for a C note. So let's 512 hertz. So let's take that to be true. Okay, so 512 hertz. Right, here we go. Let's switch the camera over. Lab mode here. Right there. I need to figure out the first place this is going to resonate. This one's too long. So back to the side. Hammer. All right, where's this going to resonate? You guys hear that? I don't know if you can hear that on camera, but this is, I'll mount the sound. It goes like, whoa, 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 whoa. Okay, that's what you guys can hear in the class, right? So, right there, that's exactly where it's resonating. You guys see that? Okay. So, let's see what distance that is. That looks like 15 centimeters. 15 centimeters. Okay. Now in meters, that's 0.15 meters, isn't it? Okay. Everything's in base SI units, 0.15 meters. I need to figure out the next place it's going to resonate. Approximately what factor, what multiple of 15 centimeters is going to be the next resonating place? 3, yeah, it should be approximately 3 times as much. Maybe not exactly, but pretty close to. Like if you're looking for like a sort of rule of thumb. So should be about 45 centimeters in. Let's see. Here, right there. That's it. That's it. What is it? 49. Ooh, tricky. 49 centimeters. Okay, which was pretty close to 45. So it's good. 49. So it's 0.49 meters. You got this. Now that you got those 2 lengths, next step is to take the difference. So what is 49 centimeters minus 15 centimeters? We're looking at 34 centimeters. So that'd be 0.34 meters. Okay. Now, remember that that difference represents half a wavelength. So you have to double that to get the full wavelength. That's 0.68 meters. Right. Okay, so that's interesting. That sound that you guys have been hearing has a wavelength of about 68 centimeters. All right. If you can see like the air molecules like bunching up, what's going to be those intervals. All right, last step. Speed is equal to wavelength times frequency. So let's take that wavelength of 0.68 meters and multiply by that frequency stamped on the tuning fork of 512 hertz. That is, hey, 348 meters per second. 348. That is extremely close to the textbook value. We said it should have been in like the 340s. Yeah, and it totally is, isn't it? Okay. And I was just recording to 2 sig figs, the nearest centimeter. So that worked out really well. Right, let's try this with a couple other tuning forks. So if you flip the page over, next one I'm going to pull out of the box is the one that says B, and it says 480 hertz. So let's do that. Let's do 480 hertz. But we'll do the same procedure we just did. Right there. So fundamental frequency, I'm getting 17 centimeters, 17. So it's 0.17 meters. A factor of 3 would be about 51 centimeters. So that's where I'll hunt for the next resonating location. Be pretty close to that. Or this change for. It's right there. Oh, it is 51. Huh. Okay. I think that's the first time all day that it's been an exactly multiple of 3. Okay, so 51 centimeters. If you take the difference, it should be 34, I think. Right. 17, so 0.34. I think that's right? Yeah. And then if you double, oh, interesting. If you double that, you get the same wavelength as we got on the other side of the paper, don't you? Yeah. Now, it shouldn't have been like, ideally, should this wavelength have been longer or shorter than the previous one? Hold on. Here's the first one. Here's one we just did. Like a drop in tone.
Yeah, it's short, very long.
Should have been a long wavelength. Yeah, exactly. Okay. So okay, whatever. That's what we get. So we'll run the numbers. Okay, last step. Wavelength times frequency to get the speed. Wavelength of 0.68 meters times the frequency of 480 hertz. 326 meters per second. I'll take it. 326. That's pretty close. What is 326 divided by 343? About 95%. Okay, so maybe we were off by about 5%, which not too shabby. Let's do next tuning fork. This one says A, but it says 426.6. I think they went super precise with that because by a different definition, it should be 440, but we got 426.6 hertz. Okay, last one. Right there. centimeters. So for 426.6 hertz, it was 0.20 meters. So if you're watching the video, this is where you got so far. Now 3 times that is about 60 centimeters. So break out the double pipe. Alright. All right, now this one's real subtle, but I think it's pretty close to there. How accurate this one's going to be. Again, 62 centimeters, 62. Switch the camera back. Its last measurement. So 0.62 meters. The difference is 0.42. Since that's half a wavelength, double that to 0.84 meters for the full wavelength. And speed is equal to this wavelength, 0.84 meters, times this frequency of 426.6 hertz. I'm looking at 358 meters per second. What is that compared to 343? That's about 1.04, it's about 4% above. Okay, so not too bad. The first one we did was looked extremely accurate according to the textbook value. The second one was about 5% under. The one we just did was about 5% over. Yeah, I'm really happy with those. I think that worked out really well. Right, so here's what we do with this lab. I'm not actually going to pick up this paper, so hold on to this for your own reference. Maybe study that. There could totally be an AT question about that. But I'll give you guys credit for it. So I'll put you guys points in the grade book as long as you're here, follow along. Okay, next thing. I'm going to go hit this very last college physics problem, the last main one that I assigned to you guys. So this is number 46 from chapter 14. This one involves an equation that you guys have not seen yet. Anyway, so some new information. What do we got here? I got in the arrangement shown in this figure, an object mass 5 kilograms hangs from a cord around a light pulley. The length of the cord is 2 meters. So from here to here, it's 2 meters is L. When a vibrator is set with the frequency of 150 hertz, so this vibrator is like bouncing up and down 150 times per second, which is crazy fast. A standing wave with 6 loops is formed. A standing wave. Hey, you guys saw a video demo that was almost exactly this. You guys saw a vibrator, some standing wave. Now, guys, if there's 6 loops, 1, 2, 3, 4, 5, 6 loops, just like the picture. How many wavelengths is that? 3. Yeah. 1, 2, 3. So if you ever do this lab in real life, maybe go to college and do this lab, then yeah, something like that. I remember the wavelength is the number of wavelengths is half the number of loops. Okay. What should be the linear mass density of the core? Ooh, okay. Linear mass density, like how many kilograms per meter is what we're going to calculate. Okay. Think of this. If it's a real skinny string, it's probably a little bit of mass per unit length. If it's a real fat string, there's probably a lot of mass per unit length. That's what linear mass density is. There's also a couple of follow-up questions, but let's do that one first. Okay. Now the trick here with this one, I need here we go. Okay. This involves a formula that I have not shown you guys yet, but I want you guys to at least see this before you walk out of this class. It goes like this. Let's zoom that out. The speed of a wave on a string is equal to the square root of the tension force divided by linear mass density. Now, I don't do this very often, but I'm going to spell out these variables because, so V in this context represents the speed of a wave on a string. Okay, so maybe you have a string, it's pulled out, there's some, it's taut, and you pluck it, and there's like a pulse. Like how fast is that pulse moving? Well, if you knew the tension of the string and you knew the linear mass density, I bet you could calculate it. Like this. So F sub T represents the tension in the string. Last semester, I was using capital T for tension, but in this chapter, you gotta be really careful because capital T could represent time period. So it's probably safer to just do F sub T for tension, like tension force. Okay. And mu, you guys have seen mu, at least in a couple of contexts in the past. As a prefix, it's micro, like 1 million, 10 to the minus 6. Or you guys have seen this as the coefficient of friction. Okay? But in this context, it's neither of those. In this context, it's linear mass density. Again, if you're comparing like a real skinny string to like a real fat string, okay, what's the mass per unit length? Okay. So what are the units on these? Speed would be meters per second. Tension is going to be in newtons, and linear mass density might be like kilograms per meter. Yeah, you see like grams per meter, but kilograms per meter. Okay. Good for that. To answer the, I'm eventually going to get back to that textbook question, but we also got to to answer that question, you need to know one more thing, which is the formula we've been applying to this lab. Speed is also equal to wavelength times frequency. Okay, because the setup, I'm going to switch back to it, is that they told us what the frequency was. We can figure out the wavelength based on the length of the string, the number of loops, so you can get the speed that way. And if you know the speed, I mean, this speed is equal to this, speed is also equal to this. We can connect it back to this, right? Okay. So we're looking at this type setup, right? Remember, 6 loops means 3 wavelengths. And since the full length of the string was 2 meters, wouldn't each wavelength be 2 meters divided by 3, which is like 2/3 of a meter, right? So that should be like 67 centimeters, like 2/3 of a meter. Right? So the question is, what is linear mass density? So we're trying to chase down this right here. How many kilograms per meter is that string? And it should be a tiny, tiny number, right? And we're talking about a string. So kilograms per meter, it should be a tiny number. Right? So we can put it all together. I'm going to start with this. Actually, let me do I'll substitute in terms of variables. If V is this and V is that, couldn't I say this? Wavelength times frequency is equal to square root of tension force divided by linear mass density. Okay. I'm trying to say a different way than I solved it earlier. Also different from the solution I have. If you look up the solution printed online, I used a different method that leads to the right answer, but I think it's kind of confusing. So this is probably the best way. Let's solve in terms of variables because that's good practice, right? Maybe square both sides. So this squared is equal to tension force divided by linear mass density. Cross multiply linear mass density, divide down all that squared stuff. So this is going up, this is coming back down. Okay. Cross multiplication, sorry. So looking at linear mass density should be tension force divided by wavelength squared times frequency squared. Okay. I think that's valid. We'll find out. I know I've got the answer in front of me, so we'll try. Okay. Now the tension force, okay, shouldn't the tension be provided by the hanging weight? And if this was, so really this piece right here is mg, isn't it? Mg. Okay. And if this has a mass of 5 kilograms, then what is its weight in newtons? 50 newtons, right? 50 newtons of force. Okay. Let's go and plug in numbers. So tension, which is provided by the weight, I'm looking at 50 newtons of force. The wavelength, well, remember the length of the string was 2 meters, but there were 3 full wavelengths. So it should be like 2/3 of a meter. That's getting squared. And the frequency was given as 150 hertz. Don't forget to square that. Okay. So I think this should give us the correct answer. Is that okay? So back up, full picture. There was a big old rig going on. There's some geometry. You had to figure out that the wavelength is 2/3 of the length of the string. You had to figure out that the tension was provided by the weight. And then you had to combine 2 formulas. Speed equals wavelength times frequency, which you guys have seen quite a bit. But also this one that is new as of today, speed on a string is equal to the square root. Okay. So you can put that all together, like a bunch of puzzle pieces, pop, pop, pop. Let's see what we're going to get. What's 50 divided by 2/3 quantity squared? Well, need more stuff in this denominator. Go back and insert some more parentheses. Okay. Times 150 hertz being squared. I'm looking at, yeah, that's the right answer. 0.005 That's kilograms per meter, if you follow the unit, because linear mass density, mass per unit length. There you go. And if you like, you could also call that 5 grams per meter. Right? Maybe that's a bit more intuitive to work with. And talking about a string, so really small linear mass density, right? Guys get that? Right, so if AP asked anything like that, they would definitely have to give you this formula. But everything after that would be fair, I think, because it applies critical thinking, figure out how do formulas interact with each other. There are a couple of follow-up questions, so let's knock these out. How many loops would result if m is changed to 45 kilograms? Okay. This is a proportional question. Remember how the original mass was 5 kilograms? They're up it up to 45. Guys, 5 to 45, that's increasing by a factor of what? 9. Okay, let's see if we can follow this formula and figure it out from there. How many loops would you form? Okay. Now, loops, that's sort of a wavelength question. Right? Maybe I'll go back to this version right here. I think this version is probably the easiest way to answer this. Okay. So linear mass density is just whatever it is for the string, property of the string. The frequency, well, that oscillator is still maybe bouncing up down 150 hertz. Okay. So if you increase this tension force by a factor of 9, which you would, right? Mass goes up by factor 9, weight goes up by factor 9, tension goes up by factor 9. What's the square root of 9? 3. And on the other side, to balance that equation, wavelength must be increasing by a factor of 3. You guys see that? If the tension goes up by a factor 9, wavelength has to increase by a factor 3 because the F and the mu stay the same. Okay? So you got 3 times the wavelength. Hey, if you have 3 times the wavelength, go back to this picture, what's that going to look like? How many wavelengths would actually be sitting right here? Exactly 1. Remember, there were 3. We got wavelength, wavelength, wavelength. If the wavelength increased by a factor 3, they're just going to have 1 wavelength. Wouldn't that be true? You draw what that would look like. You'd have your oscillator right here. Have the pulley, the 9 times the mass here, 9 mass. Okay. And this would be bouncing up and down. Okay. Isn't that 1 full wavelength? And how many loops is that? You see 2 loops, right? So 1 wavelength, 2 loops. Okay. There's one last question. Part C. How many loops would there be if m was changed to 10 kilograms instead? Okay. Well, that's a factor of 2 from the original. So from 5 to 10, that'd be a factor of 2 in this, right? So let's do the same analysis we just did. Factor 2, square root of 2, is that like 1.414? Which is not an integer value. So wavelength would increase by 1.414. Is that still going to be a standing wave even? No, it's just going to be all like muddy. You might see some pulses maybe racing back and forth or something like that, but it's not going to be a standing wave. There's going to be no nodes. So the answer is that there would not be a standing wave. Okay? There'd be no standing wave, no loops, nothing like that. Okay. Guys good so far? Right. Stick here. Okay. Let's switch over to AP Classroom.